Now, a beautiful concept called atomic spectrum. This is a dispersive medium, a prism. You know why prisms are used. If composite light passes through the prism, then radiation is split according to frequency or wavelength, which is called spectrum, isn't it? Now let me show you the schematic representation of obtaining spectrum. This is a source, filament lamp, tungsten filament lamp. This is a cardboard, and here cardboard is cut. This is cut portion, which is called slit. So there is a slit in the cardboard which will allow light to pass, and all other light are cut off by the cardboard, isn't it? Now when light passes through the slit, and falls on the dispersive medium, then if this is composite light, white, since I can't show white line, so I'm using this color. If this is white light, then this splits into constituent colors. At the second phase, again the light splits, so we can see all colors. So these colors were there in this white light. And you know, for white, like sunlight, this pattern goes from violet to red. VIBGYOR. Violet, indigo, blue, green, yellow, orange, red. Violet is most deviated, red is least deviated. Okay, done. So on the screen we find different colors. This colored pattern is called spectrum. Spectrum means arrangement of something according to some parameter. Here, arrangement of light according to frequency or wavelength. So that is why it is called light spectrum. This is glass chamber. This glass chamber is filled with suitable gas in atomic state. It should not be in molecular state, atomic state. If this glass chamber is suitably excited with plus and minus potential difference, electrical energy, then this gas starts glowing. When it starts glowing, that light is made to pass through the prism. So let us try to get spectrum of the light emitted by the excited gas in atomic state. Okay, so what we get is this spectrum, and this spectrum contains few colors. Observe this. This is the spectrum. You can see dark background and bright lines. These bright lines represents all those radiations which are emitted by this excited gas. So we can see lines. So that is why this is called line spectrum. So what is the nature of line spectrum means? Bright lines appear on dark background, and this line spectrum is due to emitter in atomic state. So this is also called atomic spectrum. Atomic spectrum. Okay. Suppose this chamber is filled with gas in molecular form. If gas is in molecular form, carbon dioxide, carbon monoxide, nitrous oxide, similar gases, and if that gas is suitably excited, then the emitted light is made to pass through dispersive medium, and pattern is obtained on the screen. And the pattern will have bunch of lines. Bunch of lines looks like bands. So it is called band spectrum. Band spectrum is due to molecules, also called molecular spectrum. So what is molecular spectrum means? The spectrum of light emitted by the emitter in molecular state. Now observe the pattern. On dark background, bright bands are obtained. Bands means it is bunch of wavelengths. So if we draw lines like this, very close to each other, then it looks like band. So this is band spectrum. Band spectrum. Suppose tungsten filament, sun, or black body. Last year you have read about black body radiation. If light from black body or sunlight is made to pass through a dispersive medium and spectrum is obtained, we find almost all colors. We find almost all colors means this is how the spectrum looks like. You can find almost all wavelengths, almost all colors, ranging from violet to red. So this is called continuous spectrum. Continuous spectrum is characteristic of black body. Okay. So this continuous spectrum is represented by this graph in first PU, a graph of intensity versus wavelength. See, all colors are present means all colors are present. So this is continuous spectrum. This is also called black body spectrum. So continuous spectrum is due to black body. Of course, with lower resolution, sunlight also gives continuous spectrum. With high resolution, it is not continuous spectrum. Please note, with high resolution, sunlight is not continuous spectrum. Next, gas in atomic state gives line spectrum. Bright lines on dark background, also called atomic spectrum. If emitter is in molecular state, then band spectrum, also called molecular spectrum. This is spectrum of hydrogen. Students, can you guess the nature of spectrum or the type of spectrum? Dark background, bright lines means emission spectrum, line emission spectrum. This is another line emission spectrum of helium. Now, absorption spectrum. Spectrum should be observed after absorption. Okay. Now, this is a black body. Black body means burning coal. This black body, heated black body, emits radiation. This is a glass chamber. This glass chamber has suitable gas. And this suitable gas is at low temperature. Okay. See, black body can emit radiation. You know, black body gives almost all wavelengths. This gas at low temperature can absorb few wavelengths. So this is giving all wavelengths. This can absorb few wavelengths. And remaining light should pass through the gas. And spectrum of this light is obtained. Students, how to get the spectrum of this light? Keep prism, pass light through the prism, and before that try to have suitable slit. Okay, suitable slit. This light is obtained after absorption. That is why it is called absorption spectrum. Now this light, when it passes through the prism, it undergoes dispersion, and dispersed light is observed on the screen. Look at the nature of spectrum. there are dark lines. These dark lines represent the wavelengths absorbed by the gas. The bright continuous background is due to black body. Let me explain in brief. Black body is giving all wavelengths. That gives this background. This gas can absorb few wavelengths. They can absorb few wavelengths means those wavelengths are absent here. And absent wavelengths means these are the absent wavelengths. So what is the nature of absorption spectrum means? Bright continuous colored background with dark lines. Dark lines means line absorption spectrum. Instead of lines, bands are obtained means band absorption spectrum. Band absorption spectrum is obtained when the absorber is in molecular state. Atomic state, line. Molecular state, band absorption spectrum. So these topics are required for multiple choice questions. NEET, JEE, CET, COMEDK. A small topic, empirical formula for hydrogen spectrum. Balmer's empirical formula. Balmer series means visible. Recall energy level diagram. If transitions are to the first state, then it is called Lyman. If transitions are to the second state, from higher energy states, then that results in Balmer. So in the case of Balmer, the spectrum lies in visible range. Okay. Now these are for 1 mark questions. These are for 1 mark. Balmer's empirical formula for hydrogen spectrum. Wave number, that is 1 by lambda, is given by R into 1 by 2 square minus 1 by n square. Because transitions are from higher energy states to n equal to 2. That is why 2 square. This is n. This can be 3, 4, 5, etc. Let me write. So n equal to 3, 4, 5, etc. Am I right? Transitions from 3, 4, 5, 6, etc. to 2 leads to Balmer series. And corresponding expression for frequency R C into 1 by 2 square minus 1 by n square. Only this formula is required, okay, for 1 mark. Frequency appears means it is RC, Rydberg's constant, into speed of light. If it is only wave number, it is 1 by lambda equal to R. Now, can you guess what is the wave number of first member of Balmer series? First member. For first member of Balmer series, n should be equal to 3. Implies, rearrange the above equation, 1 by lambda or 1 by 2 square minus 1 by 3 square equal to r into 4, 9. 9 minus 4, 5. 5 by 9 4, 36. So it is 5 by 36 times R. SI unit is per meter. Second, for second member of Balmer series, for second member n should be equal to 4 to 2. This implies that 1 by lambda equal to R into, since it is Balmer, pay attention, since it is Balmer, this should be 2 square minus 1 by 4 square. You simplify this, you will get 3R by 16. SI unit is per meter because it is wave number. Third, for third member n equal to 5. This implies that 1 by lambda, students try to calculate, guess the answer, 1 by 5 square. So it is 21 R by 100. So this is for third member of Balmer series. Last topic in this chapter, de Broglie's explanation of Bohr's second postulate. Recall second postulate. Angular momentum L equal to nh by 2 pi. So this was proved by or explained by de Broglie. So according to de Broglie, if this is nucleus, this is orbit, this is another orbit, allowed orbit. If these are allowed orbits, then length of this orbit should be an integral multiple of wavelength. Because if electron is revolving, then it exhibits wave nature that you have studied in dual nature of radiation and matter, isn't it? So electron in motion also possesses wave nature. It has wavelength equal to h by p. And length of this orbit must be an integral multiple of wavelength. So this is how de Broglie tried to explain orbits, and angular momentum equal to nh by 2 pi. Okay. Length of the orbit must be equal to n times wavelength of electron waves, where n equal to 1, 2, 3, and lambda is not wavelength of radiation, wavelength of electron wave. Lambda is it's quite confusing, isn't it? But still, make use of this concept. Particle in motion exhibits wave nature. That wavelength of electron is lambda. And wavelength, length of the orbit means it is 2 pi r, circumference of the circle. Length of the orbit must be equal to n lambda. But de Broglie suggested that lambda equal to h by mv implies 2 pi r equal to n times h by mv. Now collect mv and r. It is mv r equal to nh by 2 pi. We got the expression, isn't it? So mvr is angular momentum of a point mass. Here the point mass is the electron. So angular momentum of electron must be an integral multiple of h by 2 pi. And what is n? N equal to 1, 2, 3, etc. So de Broglie suggested that electron behaves like waves, and length of the orbit, allowed orbit, must be an integral multiple of the electron wave. As a result, he could explain angular momentum equal to nh by 2 pi. This is for 2 marks. Now, if n equal to 1, then this is the orbit of the electron. If n equal to 2, there must be 2 wavelengths. Then this is how the orbit of electron looks like. If n equal to 3, then this is how orbit of the electron looks like. These are not required for your syllabus, but please bear in mind this is how shape of orbits are defined according to this expression, according to this concept.